Okay, so we're going to start homework 5, which is all about Thevenin and Norton equivalent circuits. Now, if you go back and check the lectures, basically you got your Thevenin and Norton equivalents, and Norton equivalent is going to look something like that, where there's a current source, and then a parallel resistance, and then the hookup terminals, basically. So you could say is I Norton, and then R Norton. So we're going to start with our universal method, KCL, and AFCs. Well, first thing we're going to do actually is label the circuit. Almost forgot. So we have V1, V2. I'm going to call this ground. I'm going to call this I1, I2, and I3. So we're going to do KCLs. We could say that the 75 milliamp, we'll call it like I source or whatever. So 75 milliamps is our source current, and then I1 and I2 are leaving. And we have another KCL for the node V2. I1 is going in, I3 is leaving. Okay, so that's our equations, our KCLs for that. Let's do the equations for components. So 2 kilo ohm resistor, I1 is V1 minus V2 over 2 kilo ohms. I2 is going to equal V1 minus 0 over 4K. And I3 is going to be V2 minus 0 over 3K. So now we're going to do the Norton part. So in Norton, we have to make a short circuit current, calculate this. Let me do the little I. Call this ISC, which means we're going to add ISC to this expression. And we're going to begin our analysis. So, number one thing we got to realize is when we make this short right here, that's going to make V2 equal to 0 volts because there's going to be the same voltage across here. Can you consider the short kind of like a 0 ohm link, or just it's a piece of wire kind of. So when you do that, V2 is also, when V2 goes to 0, that makes this go to 0, which means that this goes to 0 in our original equation, and we can say that I1 equals I short circuit. So if we can calculate I1, then we'll be able to calculate I short circuit in one fell swoop. So let's go ahead and take the 75 milliamps, our first KCL, and then put our equations for components in. So V1 minus V2 over 2K plus V1 over 4K. Now remember, V2 goes to 0 when we have the short. So we're going to multiply everything by 4,000 for the 4 kilo ohms. So 75 times 4 is 300. So 300 volts equals 2V1 plus V1, which means that V1 equals 100 volts. So now we can go ahead and calculate I1, which is our I short circuit. So that's going to be 100 volts minus 0, which is V2, divided by 2 kilo ohms, which is going to be 50 milliamps, I think. 100 divided by 4,000 or 2,000. 100 divided by 2,000 is, 50 milliamps. Okay, so now that we have I short circuit, we have I Norton. And now we can calculate the equivalent resistance, the R Norton. So to do that, we're going to redraw the circuit. Have this right here. Here's a 2K, 3K, 4K, and the current source is going to become an open circuit, infinite impedance, and we're going to calculate the R equivalent. So to do that, pretty simple. Here's 2 in series, 6 kiloohms. So 3K in parallel with 6K is going to equal 2K. So our Rn is 2 kiloohms. So the Norton equivalent circuit is going to look like this. We're going to have a current source, that's our ISC, and then our Norton. So we can say 50 milliamps and 2 kiloohms. And there we go. We have the Norton equivalent circuit for this problem 1. Okay, so once again, we're going to go ahead and find a Norton equivalent circuit for this. And we're going to start with our universal method once again. So KCL, actually, let me label the nodes. So there's a node, and there's a node. Okay. So I'm going to call these currents, say this is I1. Let me redraw the arrow because it's kind of ambiguous. I1. I call this I2 and call this I3. All right, so we're going to start with our KCLs. Oh, let me label these nodes first. So let me call this ground. Call this is going to be 30 volts up here if we turn that into ground. So 30 volts, and call that V1. So to do this, we got, I'll start with the 30 volt node. We have I1 leaving, I2 leaving, another current, we call it I4, I4 leaving. Well, it's not necessarily leaving, but we'll just say that, since it's a higher potential, I'm going to say that this is I4. So KCL, we're going to have 30 volt node, we have I4 coming in, I1 leaving, I2 leaving, and 8 milliamps leaving. So we already draw that because it's a bad 8. And then we're going to do the KCL for node V1. We have I2 going in, 10 milliamps leaving, and I3 leaving. We're also going to have I short circuit. So here's ISC. I'm going to add that back in. Now we're going to do equations for components. So I'll put them over here. EFC. I1 is going to be 30 volts minus 0 over 20 kiloohms. So that's going to be, I think, 1.5 milliamps. Double check 30 divided by 20,000. Yeah, that's 1.5 milliamps. So once again, I2 is going to be 30 volts minus V1 over 15 kiloohms. And I3 is going to be V1 minus 0 over 30 kiloohms. Okay, so I believe that is all our equations. Now let's go with this. Let's get to the solving. All right. So I'm going to go ahead and notice that if I short circuit connects here. That's going to make V1 equal to 0 because this is 0 volts over here. So that's going to make this 10 to 0. That's going to go to 0, which means that I3 is going to 0, and I2 is going to be, I2 will be 30 divided by 15K, so I think 2 milliamps. Okay. So now we're going to calculate I4 pretty easily. So it's not necessary, but I'll do it just real quickly. 1.5 plus 2 plus 8 equals 11.5 milliamps. Okay, so what's important is we want to find out what ISC is. So we know what I2 is. So I2 is 1.5 milliamps, or sorry, 2 milliamps. My mistake. 2 milliamps equals 10 milliamps plus ISC. Now for that to be true, ISC has to be minus 8 milliamps. So that means that it's going opposite of the direction of the little arrow we drew. And now we're going to do, now we have I Norden, let's say, or IN here. Now we're going to do the equivalent resistance. So to do that, we're going to open circuit for the current sources, and we're going to short circuit the voltage sources. Okay, so 30K, 15K, and 20K. Now we can right away, let me finish drawing this out just so you don't get confused. I got that current source open. Here's A, here's B. So right away, this is shorted. There's no voltage across it, so we just have 15 in parallel with 30K. So 15 parallel with 30K. I believe it's 10K. Let's do it real quick. Plus 1 over 30,000. Yep, that's 10K. So that's going to be our Norden. So the Norden equivalent circuit is going to be, let me draw this current source, that's ISC. I'm actually draw it the opposite direction for the arrow. So 8 milliamps. And then in parallel with 10 kilo ohms. And there we go. Simple as that. Okay, for 4.73, we got a galvanometer right here sitting inside the circuit. And initially there's 0 current flowing through it whenever this Wheatstone bridge is balanced. That's because the ratio of these resistors is the same. So this is going to end up being 5/6 of the supply voltage. And this one also going to be 5/6 of the supply voltage, which in this case is 5 volts. So if there's no difference across the sort of internal resistance of the ammeter, which is a galvanometer, it's a type of ammeter, then there will be no current flowing through it. So we want to find out what happens if we change R3 to 501 instead of, if we change resistor 3 to 501 instead of 500 ohms. So To do that, we're going to find the Thevenin equivalent circuit for this circuit, and we're going to plug our ammeter back into that equivalent circuit, and we're going to find out how much current is flowing through that 50 ohm resistance. So we're basically going to replace the ammeter, the galvanometer, with this open circuit here. We're going to solve for the Thevenin equivalent. So first thing I want to do, my bar notes, call this VA, VA and VB, these two nodes. And I'll call this 5 volts. So, I'll call this ground, which makes that 5 volts. So now we're going to do KCL EFC stuff, right? So I1 is also I1 because there's no other path for the current to flow. I2, also I2. So we can do a KCL if we really want to, but KCL is not really necessary because I1 equals I1, I2 equals I2. That'll come in handy in a second. So EFC, we have 5 volts minus VA divided by 100 equals I1. I1 also equals VA over 501. I2 equals 5 volts minus VB over 1K. And I2 also equals VB over 5K. That's VP to ground. So let me make sure that that's a B. I know it's a B, but I want to make sure that you guys know it's a B. Oh, before I move on, I should also write that the V open circuit, we have the plus over here and the minus over here. So that means that V open circuit equals whatever VA is minus VB. Okay, so now we're going to calculate what VA and VB are. To do that, we're going to use our two KCLs that we didn't really have to do, but it's because I2 equals I1, or I mean I1 equals I1, blah, blah, blah. So if we set I1 to equal itself, 5 minus VA over 100 equals VA over 501. We're going to get 5.01 times 5 minus VA, and that equals VA. So I'm going to move VA to the other side. That means that VA equals 5.01 divided by 6.01 times 5 volts. So that is going to be, let's see, 5.01 divided by 6.01 times 5 is 4.168 approximately. So we're going to do the same process for calculating a VB. To do that, we're going to do 5 minus VB over 1K equals VB over 5K. It's going to end up being VB is 5/6 of 5 volts. So 30 divided by 6, or sorry, 25 divided by 6. That is 4.167 volts. Okay. So now we know these, I'm rounding this. These are both being rounded. So I'm going to use the calculator values to calculate VOC. So VOC is going to be VA minus VB. So 4.168 0.5 blah, 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 minus 4.1666 repeating. I end up with the voltage difference being 1.38. 1.386 to the minus 3 volts, or 1.38 millivolts, we can say. Let me say, yeah, just 1.38 millivolts. Anyway, so we calculated VOC. Now we got to calculate our Thevenin. So to do that, we're going to redraw the circuit. We're going to turn off the independent sources. And to do that, let me first draw the resistors. To do that, we're going to short the voltage source. Here's terminal A, here's terminal B. 501, we have 100, we have 1 kilo ohm, 5 kilo ohms. So these two are going to be in series. 1.1K, also in series, so 5.501K, and 1.1K in parallel with 5.501K is going to be 916.69 ohms, and that's going to be our Thevenin. So we're going to plug that back into our original, or into our Thevenin equivalent circuit. So we have 916.69, that's our Thevenin. V Thevenin is going to be 1.38 millivolts. And we're going to hook up our 50 ohm galvanometer. And we're going to find out what I is. So we're going to use Ohm's law. So I is going to equal V Thevenin divided by R Thevenin plus 50. So let's go ahead and do it. So 1.38 to the minus 3 divided by 916.69 plus 50. I end up with 1.428 microamps, or times 10 to the minus 6 amps. And we could do that same deal if we did the voltage divider equation and just plugged in that little bit right there. So there you go. That's the answer. It's pretty simple. All you have to do is just remember these ratios. For 4.75, we're going to have to do something a little bit different because this dependent source messes it up a little bit. You can't find our northern the same way as we did before, where we shut off all the current sources and made the voltage sources into shorts. So instead, we're going to have to calculate both V open circuit and I short circuit and use Ohm's law to determine the Norton equivalent resistance. Anyway, I went and wrote out the equations for components in the KCL already with a little bit of simplification for the first KCL. Anyway, let's go ahead and call this ground to 80 volts. Call it V1, call it V2. Alright, so I'm going to go ahead and short this, find our I short circuit current. So it's going to make this 0 volts. So anytime we see V2, it's going to be to 0, so I3 goes to 0, that goes to 0, because 0 plus I short circuit. So if we can find I2 and I sigma, then we will find I short circuit. So to find our short circuit, we're going to need to find V1. So I'm going to use the other KCL to do that. So I already have 0.8 I delta, which is that first equation is the same equation. I just simplified it by getting rid of the extra 0.2. 0.8 I delta equals I1 plus I2. So that means 4/5 of I delta, which we already have we have an equation for right here. So we're going to multiply by 4 and divide by 5. So 4 times 280 minus V1 over 5 times 2k, which is 10k, equals V1 over 2k plus V1 minus 0 over 2k. So simplify this, we're going to get 10 V1 on the other side, I think. Yeah. So 4 times 280, let me figure that out quickly. 4 times 280 is 1120. Okay. So 1120 minus 4V1 equals 5 or 10V1 because 5V1 plus 5V1. So 1120. Let me double check. Let's see. We're going to add that. Yeah. Okay. So we're going to add to the other side. We're going to have, or add 4V1 to both sides and then divide by 14. So V1 is going to equal 1120 divided by 14, which is 10 plus 4. So that is 80 volts. So now we can find I short circuit. I short circuit is going to be 0.2 or I2 times 0.2 I delta, which we already know is 4 over 10k. So 4 times 280 minus 80 divided by 10,000 plus I2, which is V1 over 2. So 80 volts divided by 2 kilo ohms. All right, so 4 times 200 is 800. 800 divided by 10,000. Did I make a mistake? Let's see. 280 minus V1. Okay. Let me double check because let's see. 10k divided by 2k is 5. Okay, I1, I2. Yeah, so V1 makes sense. Let me just make sure I'm doing this right. Oh, I know what I did. I did 0.2. I did 0.8 instead of 0.2. So yeah, it should be 200 divided by 10,000. I think. Let's see. Because it's 0.2, which means divided by 5. Yeah, so 280 minus that. So this could be 20 milliamps plus 80 divided by 2,000, which is 40 milliamps. So I short circuit is going to equal 60 milliamps, which means I Norton equals 60 milliamps. So I'm going to pause this real quickly, and I'll be back. Okay, so now we're going to go ahead and solve for the V open circuit, the V Thevenin, so we can find I Norton, or R Norton. Anyway, I copied the equations down from the last one. Let me make sure that I use the same names for the current. I think I did. Yeah, I2, I3. So since we're not going to have that short anymore, V2 is going to equal V open circuit because we have B over here, and then the A. So we need to find that, what V2 is, and then we'll know everything else we need for this to work out. So we're going to use our standard analysis techniques. This one is going to be kind of annoying to do by hand, so I'm going to end up using my calculator once I set up the equations. So let's go ahead and do a KC, or use this first equation right here, which is the same as the other one. It's just I simplified it a little bit. So anyway, 0.8 I delta, that's going to be 4/5. So 4 times 280 minus, which we already know is 1120. So I'll just write in 1120. 1120 minus 4V1 divided by 10,000 equals I1 plus I2. So I1 is V1 over 2K, and I2 is V1 minus V2 over 2K. So I'll multiply everything by 10K, and I get 1120 minus 4V1 equals 5V1. Well, it's going to be 5V1 times 2, so 10V1 plus, or rather minus 5V2. So let's go ahead and put them all on the same side. We'll say that minus 14 V1 plus 5 V2 equals negative 1120. I'll put that as equation 1. Let's go ahead and do the same thing for the second KCL. So I2 is V1 minus V2 over 2K plus 0.2 I delta, which is 1120, or no, 280 minus V1 over 5, or 1/5 times that whole thing. So 2K divided times, or 2K times 5 is 10K, and I3 is V2 over 5.6K. So I'm going to simplify everything. Oh, let me actually scroll down. Then I'll simplify. So I'm going to find a common denominator between these two real quick. So 5.6 times 10, 56. Yeah, it's a round number. So let's make everything, multiply everything by 56,000, or 5 points, whatever 5.6. I think it's 5.6, 56. Multiply everything by 56 million. That's just going to get rid of everything. So it's going to be 56 million divided by 2,000. It's 28,000. V1 minus V2 plus 56 million. That's going to be divided by 10,000. 5600 times 280. 156,800. Don't worry about these big numbers because it's just because of the denominator. Let's see, minus V1 times, so it's going to be 5600 V1 equals 5 points. I think it's going to be a million. 56 million divided by 5.6 1,000, 10,000, not a million. So 10,000 V2. So I'm going to simplify all of that. I'm going to have 28,000 minus 56,000, or 6,600. So 2240 V1 minus, let's see, 38,000 V2. Equals negative 156,800. Punch it into the calculator. Minus 14 plus 5 minus 1120. 22400 minus 38000 minus 156,800. Okay, my calculator is giving me V1 equals 120 volts and V2 equals 112 volts. This is equation 2. So our system of equations is solved, and now we know that V2 equals V open circuit. So to calculate our Norton, we're going to take V2, which is V open circuit, 112 volts divided by 60 milliamps, which is I Norton, I believe. Let me scroll up just to make sure. Yeah, I Norton. So 112 divided by 60 times 10 to the minus 3 is about 1.8 kilo ohms. So 1.86. Okay, I'll just write that. So our Norton equivalent circuit is going to be this 60 milliamp source in parallel with this 1.8 K resistor. Here's A and here is B. There we go. We just have to remember that whenever we have a dependent source, we're going to have to use a different method than just cutting out the sources to find out REQ. Okay, so this one is a little bit similar to the last problem, where we don't have a way to directly calculate the Thevenin equivalent resistance because of this dependent source right here. But we also, there are no independent sources in this circuit. So if we were to go through everything, all these voltages are going to be 0 unless there's something attached to these terminals. So we have to apply a test source. And since we're doing a Thevenin equivalent, we have this voltage over here. So to find the R Thevenin, if we can find V Thevenin to be open circuit, we're going to give a test current, which will be our ISC. We can find R Thevenin and make the model for our circuit. Okay, so what I'm going to do is I'm going to apply a test. Sorry, let me do that again. Come on. I don't know what just happened. OneNote, why are you bugging? Okay. There you go. So I'm going to apply a test current. I'll call this current. I'll just say it's 1 amp. Doesn't matter. But I'm going to take 1 amp because 1 makes the math a little bit easier. Okay, so that means we have a new KCL. And our new KCL is going to be 1 amp entering, I2 is entering, and I delta is leaving the node V2. So let's go ahead and see what else we can simplify. Well, since I took this as the ground reference, that makes this voltage in the middle 250 I delta. So if we can find 250 I delta, we can plug that in for these values. So 250 I delta is going to be 250 times 150, or divided by 150 times V2 minus V1. That's coming from that expression I delta right here. So that's going to be 25/15, so 5/3. So 1.67 V2 minus 1.67 V1. Okay, so let's go ahead and start doing the analysis. I'm going to start with the first KCL equation, so I delta, I1, I3. So I delta is V2 minus V1 divided by 150 plus 1.67 V2 and another minus V1, so this becomes minus 2.67 V1 divided by 200. And then that's going to equal I3, which is V1 over 100. So I'm going to multiply everything by 600. That'll get rid of all the denominators. And also get rid of our 0.67. Turn it into a nicer number. So 150, or 600 divided by 150 is 4, so 4 V2 minus 4 V1. Let me move this down. That's not moving it down. Just move that down so I have enough space to write. 4 V2 minus 4 V1 plus 1.67 times 3 is 5, so 5 V2, and I think this is 8, yeah, minus 8 V1 equals V1, so 6 V1. Simplify this even more. We're going to get, let's see, we get, if I put 18, or not 18, 8 on the other side, that's 14 plus 4 is 18, so 18 V1. I'm going to put them all on the same side, so equal to 0. So 9, or 4 plus 5 is 9, so 9 V2 equals 0, and that's going to be equation 1. Let's go ahead and do find another equation so we can find the other unknown. We have another KCL, so 1 I2 I delta. So 1 plus I2, which is 250 I delta, so 1.67 minus V2, so that's going to be 0.67 V2 minus 1.67 V1 divided by 50 equals I delta, so V2 minus V1 over 150. V2 minus V1 over 150. Multiply everything by 150. I get 150 plus 3 times 2/3 is 2. V2 minus 5 V1 equals V2 minus V1. We pull that down again, just so I can write the other equation next to it. Okay, so let's see. So I keep the constant on that side. So I'm going to write 150 over here. Minus 6 V1? Or no? No, we're going to add 4 V1. Or 5 V1, so it's going to become 4 V1. And then move V2, so minus 1 V2 equals 150. I'll punch that into my calculator. See, 18 minus 9 equals 0. 4 minus 1 equals 150. Okay, so I get V1 equals 75 and V2 equals 150. Okay, so we only needed V2, but we got both of those from this just because of the way the analysis worked. Anyway, now that we have V open circuit, which is V2, we also have I short circuit, which is the test current. So we can calculate what the Thevenin resistance is. So our Thevenin is going to be V2. Oh, we do it again. So V2 over our test current, so 150 volts divided by 1 amp. It's going to be 150 ohms. All right, so now we can start to draw our equivalent circuit. And since there's no independent sources in the circuit, we're not going to have a Thevenin voltage. V Thevenin is going to be 0 volts. So we can really just write the equivalent circuit as, say, here's Thevenin resistance. So 150 ohms. That's our Thevenin. You could also, if you wanted to, you could write in voltage source V Thevenin. Call that V Thevenin equals 0 volts. But either way works. You can just write the resistor or not. Well, there you go. That's the first time we had to use a test source. Not going to be the last. All right, for 4.81, we're going to do another Norton equivalent circuit with respect to these terminals A and B. And one thing to note is we don't have any independent sources in the circuit, so we're going to have to apply the test source. And since we're doing a Norton equivalent instead of Thevenin, we're going to apply test voltage. So I'm going to go ahead, I'll put that in now. And I'm going to call this 750 volts. It doesn't matter, but the reason why I want to do that will become clear shortly. Could be 1 volt, could be 10 volts. It just, you have to have some kind of source for this, some source of energy for this source, this circuit to function. Anyway, so if I select this as the ground reference, that makes this 750 volts, and this makes 250 IX. So let's go ahead and do a KCL. I'm actually going to label a current, call this one I1. And there's also going to be a current from the source, so I'll call it IS. So KCL for the 750 volt node is one I'll do first. Well, actually there's only one node we need to do it, because the other one is just the same current. So let's see, 1.5 IX is going in, and IS is going in. Those both equal I1 leaving and IX leaving that node. So let's do the equations for components. We only have 2 here. I mean, there's 4 components, but the other ones we already accounted for in the KCL and the ground reference. So let's do I1 equals 750 minus 250 IX over 500. And we're going to do IX equals 750 volts divided, or minus 0 volts divided by 750 ohms, which is going to make 1 amp. So that's why I did the 750. It's a completely arbitrary choice. I could have done 1 and then made it 1 over 750 amps, but this is just a little bit cleaner, I think. Anyway, so now let's go back to our original KCL and begin the analysis. So if you notice, there's 1.5 Ix and Ix. So we can simplify that expression, make it, say, 0.5 Ix equals Is. Well, actually, let's just put the Is by itself. I feel like that would be better. Is is going to be, let's see, Is is going to be I1 minus 0.5 Ix. Okay, so I1 is going to be 750 minus 250 times 1 over 500. So 500 over 500 is 1. So Is is going to be 1 amp minus 500 milliamps, so half an amp. 0.5 amps, which means the Is is half an amp. So now that we've done that, we know we actually do know ISC and VOC, because we put in VOC, and IS is actually ISC. So we can find out the node resistance. That'll be 750 volts divided by 0.5 amps, so 1.5 kilo ohms is our node. And I shouldn't actually say it's ISC, because if we were to, instead of putting a test source here, just put a short, there wouldn't be any current flowing through here because there's no energy sources in the circuit. But I say ISC, here it is ISC, because that's how we calculate the Thevenin resistance, or the node resistance, which is the same, which we'll see, I think, maybe in the next problem. So we're going to have, oopsie, we have no independent sources. So this is going to be a resistance, and it'll be equivalent to I node. So 1.5 kilo ohms, and A, B. That is our equivalent circuit. You can also write a 0 ohm current source, but really it's the same thing. Okay, so for 4.87, we got a variable resistor right here, and we got to find out what value for RO will produce power dissipation of 250 watts. So we can go ahead, and if you wanted to, you could plug in a bunch of different values, brute force it like a computer, or you could form an equivalent circuit like a Thevenin one, and then try the different loads that way and model their behavior. So we're going to do a Thevenin equivalent circuit and use that in combination with Ohm's law and the power law, well, not really a law, but the power formula, to calculate what values RO might work for this. So I went ahead and labeled the circuit and wrote down currents and both the equations for components and everything. We're just going to go ahead and start solving. Now, I wrote this equivalency, Ix equals Ix. This may seem redundant, but since we have V1 and V open circuit, we have two unknowns, so we need two equations. And it just so happens we have two equations that equal to each other that have both of those values. So we can go ahead and solve for the expression for V open circuit in terms of V1, and then solve for V1. So V1 minus V open circuit over 10 equals V open circuit minus 30Ix. Now we have Ix over here, but we can't simplify into it itself, because if you simplify into itself, it'll be 0. So we're going to go ahead and take that Ix. 30 divided by 10 is 3. So minus 3V1 minus 3V open circuit all over 20. Multiply both sides by 20. 2V1 minus 2VOC equals VOC minus 3V1 plus 3VOC. So there's, let's see, there are 6 VOCs, 5 V1s. So VOC is 5/6 of V1. So let's go ahead and plug that into our first KCL equation. So we're going to have, let's see, 200 minus V1 over 25 equals V1 over 100 plus V1 minus 5/6 V1 is 1/6 V1. So let me go ahead and put the 6 in the denominator. So 6 times, what's 10, right? Yeah, 6 times 10, so 60. All that, okay. So let's go ahead and simplify. I'm going to multiply everything by 6,000 just to clean up the denominators. So 6,000 times 200 is 1.2 million, I think. Yeah, 1.2 million. Don't worry about the big numbers, they'll go away soon. And 25 divided by 6,000, or 6,000 divided by 25. Oh, forgot to divide. So 200 times 240, I should say. That's 48,000. Minus 240 V1 equals 60 V1 plus 100 V1. So V1, that's 240 plus 60. So 48,000 divided by 400 is 120. So V1 equals 120 volts, which means that V open circuit is 5/6 of that, so 100 volts, which equals V Thevenin. So now we need to find the Thevenin resistance. There's a couple ways to do it. I'm going to do the short circuit current. I actually prepared another circuit already. Oops. Let me fix this. I already drew the picture. So let me just drag this up. Okay. So I went ahead and prepared KCL and everything. We'll go ahead and solve the same way. Now, in some of the previous examples, the current like this, I3, would go to 0 because the difference across the resistor would be 0. But in this case, the dependent source makes it so we have to account for that current. So we're going to go ahead and do a similar thing we did before with the substitutions. If we have 30Ix here, we have expression for Ix. That's going to be I3 equals minus 3V1 over 20. So now we just got one unknown, and we can solve for it. Okay. So let's go ahead and do I1 plus blah, blah. So V1 over 10, or I'm sorry, 200 minus V1. 200 minus V1 over 25 equals Ix, so V1 over 10 plus I2, which is V1 over 100. Okay, so let's go ahead and solve for V1. Multiply everything by 100. We're going to get 800 minus 4V1 equals 10V1 plus V1. So that means that V1 equals 800 divided by 15, I believe. Let's see. 800 plus 4 plus 4, yeah. So 800 divided by 15 is 53. Oops. 53.3 repeating volts. And now we can use this KCL to calculate I short circuit. So I short circuit is going to be Ix minus I3. So Ix is going to be 53.3 divided by 10 minus 3V1. So that's going to become plus. Right? Yeah, it's going to become plus. So minus 3 times 53 thing is 160. So 160 divided by 20 equals I short circuit. So that's 5.3333 plus H, which means I short circuit is 13.3 repeating amps. So if we want to find R Thevenin, we're going to do V open circuit over I short circuit, and that is 100 divided by 13.33 blah blah blah, which is 7.5 ohms. I'll use the R. I just like those R's, but that's 7.5 ohms. So our equivalent circuit is going to be V Thevenin, which is 100 in series with R Thevenin. And we're going to have our load RO. We're going to plug this back in now. So if we have only one current in the circuit, call it I, and I is equal to V over I times R, and R is 7.5 plus RO, so let's do power equals, oops, let's do I squared R. I squared R, and our R is, we know I is going to be Ohm's law, so 250 equals 100 over 7.5 plus RO squared times RO. Yeah, okay. So I'm going to go ahead and put this into my calculator because it's just going to become a quadratic equation. It's not exciting. Let's see what we get. So 100 blah. Okay, so the valid values for RO can be either 2.5 ohms or 22.5 ohms. That's how we can get the power dissipated by 250 watts of power being dissipated by that RO resistor. And all it took was just doing the Thevenin equivalent circuit. Okay, so for 4.92, we're going to use a principle called superposition to find the voltage V right here. Now, in a linear system like these linear circuits, you can use superposition to find things. So we're going to consider two cases individually and then add those cases together. And we'll be able to find out what the total voltage is from all the contributions. So the way we're going to do that is we're going to consider each case individually. The first case is where we shut off the current source. It's high impedance, so open circuit. And then we're going to do the math and find out, hey, what's VI? So we got another circuit here. I'll call this I2, I3, and this is also I3. I should have labeled it first. Okay. Don't really care about this voltage, but we're going to need to know it. So I'll go ahead and write as V2. I'll call this V1 with the Roman numeral 110. Call this 0. We're going to do our KCL. So KCL, I1 going in, or yeah, I1 going in, I2 and I3 leaving. And I1 is 110 minus V. Let me just call it V1 because the VI is a little bit hard to write. We'll just consider that VI at the end. So V1 over 10. I2 is V1 over 10. I shouldn't write 10. That's 5. I3 is V1 minus V2 over 2. And it also is V2 over 12. So I'm going to go ahead and set I3 to equal each other and solve for expression to get V2 in terms of V1. So V1 minus V2 over 2 equals V2 over 12, which means that 6V1 minus 6V2 equals V2, which means that V2 equals 6/7 of V1. Yeah, plus 6, 7, 6 divided by 7. So yeah, that makes sense. We're going to go ahead and plug that into the first KCL. So 110, we move it over. 110 minus V1 over 5 equals V1 over 10 plus V1 minus V2, so 1/7. So I'm going to put the 7 in the denominator. 7 times 2 is 14. And go ahead and solve for this whole thing. Okay, so I'm going to multiply everything by 70 to get rid of the denominators. 14 times 5, 70. So let's see. That's going to make this 14 times 11, 10. So 11, 10 times 14 is 1540 minus 14 V1 equals 70, or 70 divided by 10, so 7 V1 plus 5 V1. So that's 12 plus 14, 30. So 14, 1540 minus 28 or 1540 divided by 2.828. Yeah, 14 plus 12. So that means V1 or VI or V1 or whatever equals 55. So now we're going to consider the case where V2 is short. We're going to add them up at the end, where the voltage source is short. So we're going to do this again. This whole node is together. There's a node here, node here. I'll still call this V1, and I will call this V2, and I guess I'll call this ground. All right, so we got I1, I2, I3, and I4. KCL, there's I1 going in, I2 leaving, I3 leaving. Got another KCL. Let me do it this way. Four amps going in plus I4 and I1 leaving, and there's I3 going in and I4 leaving, and 4 amps leaving. Quiz for components. V2 minus V1 over 5 is I1, and I2 is V1 minus V2 over V1 minus V2 over 10. I3 is V1 minus 0 over 2, and I4 is 0 minus 12, or 0 minus V2 over 12. Okay, so now let's go ahead and start solving. So looking at this, we can find an expression for V2 in terms of V1 pretty easily using this. So let's see, V1 over 2 equals negative V2 over 12 plus 4. So multiply everything by 12, 6V1 equals minus V2 plus 48. So V2 equals 48 minus 6V1. Go ahead and plug that in for the expression. So let's see, what's a good choice for this? I4, I1. Let me do this second equation. So 4 plus I4, which is minus 48 minus 6V1 over 12, which equals I1, which is 48 minus 6V1 minus V1 over 5. So I multiply everything by 60. So let's see, 60 times 4 is 240, right? Yeah, 240 minus 5 times negative 48. So that's going to be 30 V1, and 5 times 48 is 240, or minus 240, equals 5, or 12 times that. So 12 times 48 is 576. 576 minus 7 times 12. 7 times 12 is 62, I think. 84. Not 62, sorry. Okay, so minus 84 V1. These are going to cancel out. That means that V1 equals 576 divided by 184 plus 30, which is 114, I think. Yeah, 114. So 576 divided by 114 is, let's say, approximately 5. Let's just say 5. Okay. Now, to find V1 and V2, we're going to have to consider our polarities and such. Now, I picked the ground reference over here to be 0. So that means that this is going to be minus 5 whenever we consider this little plus here. So if we can say that V2 equals the negative of V1, so that's going to be negative 5 volts. So the V that we're looking for is V from set like equations 1, I guess, and then plus V from equations 2. So 55 minus 5 is 50 volts. Now the other part of the question is saying, find the power dissipated in the 10 ohm resistor. That's easy. We know the voltage. And we don't want to bother, we're not going to bother with the current. It would be trivial to do so, but we'll just do P equals V squared over R. So 2500 divided by 10, which is 250 watts. And there we go. Not too bad. It's just a little bit tricky because of the polarities. If I had picked this to be 0 volts, this would be negative 5. So that was a mistake on my part in terms of being confusing, but it's the same math working out ultimately.